Okay, so this section is infinite series, and we want to explain what we mean by the sum of an infinite series. We want to calculate the sum of a geometric series and evaluate a telescoping series. Okay, so last time I made a big deal when I said a sequence is a list of numbers, and I meant that it is a list. When you make a list and you go to the grocery store, or you make a list of tasks, or you make a list of items, they are generally separated by a comma. So that's what we mean by a list. Okay, so these are separated by a comma. When I talk about a series is a sum. So that means we are now actually taking the terms of a sequence and summing them up. So I need to make sure you understand the difference. A sequence is a list. A series is a sum. Okay. So the sequence is just a, AN, the next term A2, A1, the next term A2, the next term A3. And you can go and you can continue, and that's an infinite series sequence, an infinite sequence. And we went through several different types of sequences. We even had a PowerPoint on different sequences and what they look like. We looked at limits of sequences in our last section. So evaluating the limit of a sequence is just looking at the nth term as it goes to infinity. So we talked about that as well. What we want to talk about now is a series, and the series is when you are summing up the elements in a sequence. Okay, so I have a definition here. Let me just check, go get my, okay. All right, so what we want to talk about is an nth partial sum. Okay, so the nth partial sum means let's just sum up only the first n terms. Okay, so we're not talking about summing up the entire series. We are only talking about summing numbers 1 through n. Okay, so the nth partial sum means summing just numbers 1 through n. Okay, so for example, here, if I look at this sequence, I have the sequence 1/2 to the n minus 1. Okay, so 1/2 to the n minus 1, this is the sequence. So the first term is n equals 0, n equals 1. So I get 1/2 to the 0 power, that gives me 1. When I do n equals 2, I get 1/2 to the first power, that gives me 1/2. When I do n equals 3, I get 1/2 squared, that gives me 1/4. And so this is what this sequence looks like until I go out. I get to the nth partial, I get to here 1/2 raised to the n minus 1 term. So that's, and then we just keep going. Okay, so this is the sequence of terms that looks like 1/2 to the n minus 1. All right, so what does it mean then for us to find the nth partial sum? All right, well, the nth partial sum says just sum up, and this is wrong. That should not be infinity, that should be n. So the nth partial sum says just sum up the first n terms. Okay, so let's see what we get. All right, so we're going to do this. So S1 says just find A1, and A1 is 1. Okay. S2 is A1 plus A2, and that is 1 plus 1/2. S3 is A1 plus A2 plus A3. So that's 1 plus 1/2 plus 1/4. Okay, so we can keep summing these up. S4 is A1 through A4. So that is 1 plus 1/2 plus a fourth plus 1 over 16. Okay, so this first one, S1 is just 1. When we get S2, we end up getting 3/2. When we add up S3, we end up getting 7/4. And then when we add up S4, we end up getting 15/8. Okay, so one of the things we can do is we can either find a formula for this, or we can keep going far enough out into the series until we kind of get an idea of what this actual series is going to sum to. Notice I am summing up the terms of the sequence. Okay, so one of the things we can do is if we look at S1, S1 can be written as 2. So if you notice, each one of these is kind of getting close to 2. S1 I can write as 2, I want to write this in red, as 2 minus 1/2 to the 0 power. S2 I can write as 2 minus, well, I'm subtracting off a half here. So this is subtracting off 1/2 to the first power. 2 minus a half is 3/2. If I take 2 minus 1/2 squared, that is 2 minus a fourth, I end up getting 7/4. And this is 2 minus 1/2 cubed. So 2 minus 1/8 is indeed 15/8. So I can see that each one of these is written as such, and we need to kind of get a pattern. So we want to keep going and see what our nth one looks like. Well, it looks to me like Sn was going to be 1 plus 1/2 plus 1/4 plus 1 over 16 plus I'm going to keep adding until I get to the last term, which will be 1/2 to the n minus 1. So that is Sn. It is the nth partial sum. Okay, so now what I want to do is, as I'm looking at this nth partial sum, I realized that I created a formula for it as we were going down. The formula in red was that Sn actually looks like 2 minus 1/2 to the nth power, n minus 1 power. Okay, so that's what Sn looks like. 2 minus 1/2 to the n minus 1 power. So this is the nth partial sum. Okay, so now what we want to do is we want to define how you actually find the limit of a sequence. Okay, so what I want to do is, if I take and write the limit, so let's look at the sum, n equals 1 to infinity of an is the same as k equal 1 to infinity of ak. So all I did was change the variable. But this is the limit as n approaches infinity of the sum k equal 1 to n of ak. But this thing says sum up the first n terms. So this is the nth partial sum. So the way to find the sum of the entire series, as it sums all the way to infinity, which we can't do, we can't keep adding it and keep adding numbers infinitely, we'd be here forever. But we can take a limit that would give us the value of the sum. Okay, so this limit then is the limit as n goes to infinity of the nth partial sum. Okay, so therefore we can define the limit as n goes to infinity. I'm sorry, that's not what I want to write. We can define the sum k equal 1 to infinity of an, ak, as the limit as n approaches infinity of the nth partial sum. Okay. All right, so we have the sum k equal 1 to infinity of 1/2 to the k minus 1 is the limit as n approaches infinity of the sum of, let me just write that, of Sn. Let me write Sn first. Of Sn, but that's the limit as approaches infinity of the sum k equal 1 to n of 1/2 k minus 1. But we already said the nth partial sum is 2 minus 1/2 to the n minus 1. Okay, so now what happens to this term? I'm taking a fraction like 1/2. When I square it, it becomes 1/4. When I cube it, it becomes 1/8. Any number whose absolute value is less than 1, when you raise it to the nth power, it gets smaller and smaller and smaller. Why? And I seem to have forgotten my limit. We said the nth partial sum was 2 minus 1/2 to the n minus 1. But this is the limit as n approaches infinity of 2 minus, and this is 1/2 to the n minus 1. So now you can really see it. All right, so it's 1/2 to the n minus 1. So now you can really see that as you raise 2 to and larger powers, 2 to a high number goes to infinity, 1 over that goes to 0. So this thing goes to 0. So the actual limit, so we can sum the whole series and get 2. Okay, so that is the limit of that series. All right. So if you can find the nth partial sum of a series, then take the limit, you will have completed and found the limit of the entire sequence. Okay, so here's a definition. So let's say we have a sequence of terms going from 1 to infinity, and we choose to sum them up. Now here's where I messed up. That should be that term should be infinity. And this term should also be infinity. Okay. So if you sum an infinite sequence and you get a number, then the series converges. If you sum an infinite sequence and you get infinity or negative infinity, which is possible, then the series diverges. Okay, so we're going to look at two series today. All right, so the first one is the geometric series. So this is the geometric series. The geometric series looks like the sum n equals 1 to infinity of AR to the n minus 1. And this is what it looks like. Some people factor out the A, it is okay. Some people factor out the A and write it as 1 plus R squared plus dot 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 plus R to the n minus 1 plus dot dot dot. Okay, so what is an example? An example of this series, an example of this might be the one we just looked at. So we might want to sum n equals 1 to infinity of 1/2 to the n minus 1. Now we already did this one using the nth partial sum. Okay, we want to also, we already showed that this one for sure we know equals 2. So this is 1 plus 1/2 plus 1/4 plus dot 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 plus 1/2 to the n minus 1 plus dot dot dot. We already showed that if you sum that infinitely, you will get 2. But how about this one? The sum n equal 1 to infinity of 3 times 2/3 to the n minus 1. Well, that one would look like 3 times 1 plus 2/3 plus 4/9 plus 8/27 plus dot dot dot. Okay, so that's what that sequence would look like when it's summed up. Okay, and we right now, for what we already know, we have no idea what that's going to be. How about this one? The sum n equals 1 to infinity. Who's writing on my board? Of 1/2 times 5/4 to the n minus 1. So this one looks like 1/2 times 1 plus 5/4 plus 25/16 plus 125/64 plus dot dot dot. Again, at present, we haven't figured out whether or not this one actually converges. Okay, so we're going to prove that this particular sequence actually converges or diverges underneath particular circumstances. Okay, so let's start with so we're going to go back to the original form. So let's consider sum n equals 1 to infinity of AR to the n minus 1. All right. So let's look at the nth partial sum. So the nth partial sum is A plus a times r plus a times r squared plus a times r cubed plus dot 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 plus ar to the n minus 1. So that's the nth partial sum of this geometric sequence. A geometric series. A geometric series always has the same form. Okay, that is the form of a geometric series. Okay, so let me just go back and highlight that for you. Uh-oh. Okay, so a geometric series is always of that form. A times r to the n minus 1. Okay, so I found now the nth partial sum. And then what I want to do is I want to multiply the nth partial sum by r. So if I do that, I get r times Sn. And this is going to give me ar plus ar squared plus ar cubed plus dot 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 all the way up until I get ar to the n. And now what I would like to do is take Sn minus r times Sn. So that is going to give me this. Okay. And then I am going to subtract off this. Okay. So I'm going to take the first one and subtract the second one. Does anybody notice anything about when I subtract them? Anybody notice anything when I subtract?
Would they cancel out?
Okay, almost everything in the middle cancels out. I have AR minus AR, AR squared minus AR squared, AR cubed minus AR cubed. And this one is actually going to cancel with the one before it, which is A. Okay, so I get Sn minus R times Sn is equal to A minus A times R to the n. So I'm going to factor out the Sn. So I get Sn times 1 minus R. And then I'm going to get A times 1 minus R to the n. Okay. All righty. So now we get Sn. This is the nth. So now we're able to solve for the nth partial sum. And I don't even know what A and R are. Okay, I don't even know what these variables are. I just know I have A times 1 minus R to the N divided by 1 minus R. Okay, I have a question. Okay, thank you. All right, so now go back to my series. This was my beginning series, my geometric series. So this is the nth partial sum of the geometric series. Okay, so here's my question. If R, let's say R is equal to a fraction, then we're raising a fraction to the nth power. And as we do that, it gets smaller. But if R is a number greater than 1 in absolute value, as we raise it to a power, it gets larger. Okay, so let's go back and see what I mean. So let's just go back and look at this for a minute. When I had 2/3, notice I got 2/3, I got 4/9, I got 8/27. These numbers are getting smaller because their absolute value is less than 1. But notice when I took 5/4, I had 5/4, which is a little over 1 1/4. I have 25/16, which is getting close to 2. This is getting closer. That is over 2. These numbers are growing. So we know if the absolute value of R is less than 1, then R to the N will go to 0 as N goes to infinity. Okay, so there we have it. So therefore the sum S, which is the sum, oh, I hate this. Oh, we'll use N equals infinity, N equals the sum, N equal 1 to infinity of AR to the N minus 1 is going to be the limit as N approaches infinity of the nth partial sum. Okay, but that is going to equal the limit as N approaches infinity of A times 1 minus R to the N, because this is the nth partial sum, divided by 1 minus R. And if the absolute value of R is less than 1, then this R to the N will go to 0. And we see that the sum of our series, there's no R left in here, so we just get A over 1 minus R. Okay, so that means for a geometric series, we now know what its sum is. Okay, so for a geometric series, we get the following. The sum N equals 1 to infinity of A times R to the N minus 1 is going to equal A divided by 1 minus R. That should be A over 1 minus R. If, and this is only if, the absolute value of R is strictly less than 1. Okay, so that's our rule. All right. If R is greater than or equal to 1, if the absolute value of R is greater than or equal to 1, the series diverges. All done. There we have it. Okay, so I'm going to block this out and we're going to take a peek at it real quick. So let's put a nice block around here. I'm going to tell you right now, there are 12 series tests we are going to do. This is number 1. Okay, so you may as well just start working with them because this is number 1. Okay, so let's go back to my series. So this first one was, here we go. So all right, so, oh boy, that's not cute, but at least it gives me Control Z. Put it over here. There we go. I got an idea of what it is. Okay, so for the first one, we had the sum n equals 1 to infinity of 1/2 to the n minus 1. So as we can see, the absolute value of a half is less than 1. So this is going to be A. A is 1 here. So A is 1. R is 1/2. And the absolute value of R is less than 1. So this is going to be A over 1 minus R. So that's going to be 1 over 1 minus 1/2, which is 2. Okay, so that takes care of the first one. And we should get 2 because we already proved that to ourselves. The second one, the sum, n equals 1 to infinity of 3 times 2/3 to the n minus 1. Somebody tell me what, actually, I'm going to take roll while you do these next 2. So that's number 2. And here's number 3. The sum n equals 1 to infinity. I forget what I had. 1/2, 5/4 to the n minus 1. Okay, so while you work on those, I am going to take roll. Does the first one converge? And if so, to what? What is R? What is A? A is what?
Would A be 3?
Mm. A is 3. R is 2/3. The absolute value of 2/3 is less than 1. So this is going to converge to A over 1 minus R. Which is 3 divided by 1 minus 2/3, which is 3 over 1/3. So that's going to converge to 9. And this one, A, is 1/2. R is 5/4. The absolute value of 5/4 is greater than 1, so this series diverges. 4, the sum n equal 1 to infinity of -1/3 to the n minus 1. Let's say 4, there we go, 4. So A is 4, R is -1/3. The absolute value of -1/3 is less than 1. So this will converge to A over 1 minus R. Which is 4 divided by 1 minus 1/3. So that's 4. The 1 minus 1/3 is 1 plus, so that's 4 divided by 4/3. So that's 3. Okay, any questions? Okay. Number 2, telescoping series. All right, so the only thing I can tell you about telescoping series is when you write out the series, all the internal terms will add and subtract each other away. Okay, so here's an example. The sum k equal 1 to infinity. Actually, I'm going to use n. N equal 1 to infinity of 1 over n minus 1 over n minus 1. Now, this looks weird, but what you need to realize here is that your an is the whole thing. It is 1 over n minus, this has to be a plus 1, minus 1 over n plus 1. So the whole thing is an, the whole thing. Okay, so your S1 is 1 over 1 minus 1/2. Your S2 is 1 minus 1/2 plus 1/2 minus 1/3. That's your S2. Your S3 is 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4. And so we can notice that on these nth partial sums, the stuff disappears. Okay, so if we were to write a formula, we would get Sn would be 1. This turns out to be 1 minus 1/2. This one turns out to be 1 minus 1/3. This one turns out to be 1 minus 1/4. So now what I'm going to find out is when I do Sn, I'm going to get 1 minus 1 over n plus 1. So therefore, the sum n equal 1 to infinity of 1 over n minus 1 over n plus 1 is the limit as n approaches infinity of the nth partial sum. But that's the limit as n approaches infinity of 1 minus 1 over n plus 1. And 1 over n plus 1 goes to 0. So this is just 1. Okay, we'll pick up here tomorrow. The next example is the sum n equals 1 to infinity. No, n equals 2 to infinity of 1 over n squared minus 1. So I hope you guys are good on your partial fractions. Okay, I will see you all tomorrow.
Have a nice day.
Have a good day.